Yes. Also, please do not be like hesitant to ask questions. I'm not exactly sure like where everyone's background is, and I'm really hoping this is like actually something you can get something out of. So ask if you want to ask. And so I guess I can get right in. I'm going to be talking about topological quantum field theories. And I put a funny little cartoon character on every one of my slides because I wanted to see if I could, and I could. Um, so, oh, there we go. Quick disclaimer, I'm not really a physicist, I'm more mathematical physics. I'm not super aware of the exact usefulness of TQFTs, but I know, at least for these purposes, TQFTs are a kind of nice candidate theory for quantum gravity because they're background independent to space-time. They're of significant interest to condensed matter people because they come up in topological orders with fractional quantum Hall and superconducting, which you may have heard some controversy about recently. And in pure mathematics, TQFTs come up as low dimensional manifold invariants, mostly 3 manifolds. Today I'm just going to be going over the 2-dimensional case because it has a really nice, simple presentation and classification. And part of that's already kind of in the title. And so the first thing I'd like to go over is just if you're not aware or you need to review some really basic category theory. So the first thing is, what is a category? We're going to have a set of objects and we're going to define morphisms, so functions, maps of some kind between these objects. And we're going to say we have a composition between these morphisms that's unique and well-defined, and we have identity morphisms. So a really common example is the category of sets. You have your objects are just sets, and your morphisms are functions from a set to a set. Groups, if you've seen those maybe in QM or mathematics, topological spaces where your morphisms are continuous maps. And a big thing we want to talk about is mapping a category onto another category. And so we're going to have functors. We map objects to objects, and we map morphisms to morphisms, and we just say that we preserve compositions and we preserve identities. Any questions about that? Okay. So our second main object is a cobordism. So we're going to take 2 manifolds. Anyone need a refresher on the manifold? Okay, so manifolds are going to be a topological space, and we're going to ask that it locally look like Euclidean space. So for one manifold, we're going to have the real line, for example, locally looks like Euclidean space because it just is Euclidean space the entire way. A circle is also a 1 manifold because locally, when you zoom in, it looks like a line. And globally, it doesn't. It has this wraparound, which makes it not Euclidean, but it's a manifold. The classic example is, of course, the Earth. When we're on the Earth, it looks like we are just on a plane. And if you kind of zoom out enough, you see that this is not actually a plane. And so for the purpose of this talk, we actually really only care about circles. So a cobordism for manifolds, it's going to be a manifold where you have boundaries or edges. And we're going to take 2 manifolds, and the cobordism between them is just a higher dimensional manifold where those edges are the previous manifold. So the simple example, if we have 2 circles, a cobordism between them is just a tube that's open on both ends. And that's actually most of what we're going to care about here as well. Yes, exactly. So your boundaries of a straw, your edges, is going to be a circle and another circle. And so we can define this cobordism category. So our objects are going to be closed and oriented n-1 manifolds. A lot of that's just details we don't have to care about. And our morphisms are going to be these things where you have boundaries being the other manifolds. Identity morphisms are cylinders, so it's just a straw. And we can compose these by gluing them. our kind of interesting thing is we have more complex manifolds than, or cobordisms, than just a straw. If you imagine a straw that kind of splits and then rejoins, has a hole through the center, it's not the same thing as a normal straw, but it's still a cobordism between two circles. And so for our talk, we're going to care about the category 2 cobordisms. So we're only caring about closed-oriented 1 manifolds. And in this case, that means we only have circles and unions of circles. So just n circles next to each other. And we're going to just ignore all the other details here because the diagrams kind of just work anyways. And so the last kind of bit of background we need is what a monoidal category is. And the details don't really matter as much as this is going to be a category with a product. In our cobordism category, our product is disjoint union, so we can put 2 circles next to each other. And we're going to also be caring about the category of vector spaces. Our objects are vector spaces, our morphisms are linear maps, and here our product is going to be the tensor product.
Can you describe what a vector space is? I have been talking about.
Yes. So a vector space, we're going to have what you can think of it a lot of the times as coordinates. So a 3-dimensional vector space could be 3 coordinates, and we're going to have some scalar field we multiply by. So that's kind of like lengths you can extend, and you can subtract, add, multiply vectors. And so with these monoidal categories where you have this product, we're going to care exclusively about monoidal functors, so a functor that also preserves this product. And this leads us into our definition of a topological quantum field theory. So we're going to map from the cobordism category to a category of vector spaces. So what this means is to every manifold in our cobordism category, in the 2D case, this is circles and disjoint unions of circles, we're going to assign a vector space. To every kind of 2B straw thing, we assign a linear map between vector spaces. And now we also ask that this respects the monoidal structure. So if we take 2 circles and put them next to each other, the vector space we assign to that is the tensor product of the vector spaces we assign to each circle. And the only other thing is, if we have the empty set, we assign the base field to it. And so for our 2D case, this means that this functor is exclusively determined by what we send the circle to, because everything else is products of circles in tensor products of the vector space. And so we'll denote the vector space we send the circle to just as A here for shorthand. And so the main interest here is what this can be. Vector spaces are very, very wishy-washy in general. When we're talking about the category of vector spaces, we could mean infinite dimensional, unpresentable spaces that have like no structure we could talk about. And so we can kind of get into that classification. But first, there's some kind of rough physical intuition behind this, like why this definition is anything that could be called a quantum field theory. And so in a kind of basic sense, our underlying manifolds we're talking about are going to be thought of as space. Cobordisms, where you kind of take and add this extra dimension, this straw, it's kind of like space-time. So this, if your circle is 2D space in this kind of low-dimensional case, the straw is now space-time. The vector spaces are the state spaces of your quantum field theory, and you kind of get linear maps out of these, which are time evolution. Like normal, sorry.
But I think that the good word and then the good word is basically out of work.
Yes, that is the kind of more higher level intuition when you get into some of this. It is distinct from string theory though. Cobordisms are not string though. sorry, one of the last things is that if we have normally two independent quantum systems and we consider their states as a whole, those states are the tensor product of their individual states, so we have that here as well. And so this kind of big part of the theory, this topological thing, is that we're asking that our quantum field theory is independent of anything like curvature of space-time. So we don't care about relativity. We don't care if space is elliptical, whatever. It's just this topological thing. So it's dimension, where it kind of wraps around on itself and whatnot. And that's where you get the background independence for quantum gravity. Any questions about that? Because I know that's like a pretty rough analogy.
Just like the way it goes in space-time, four-dimensional space, if you're able to find like another axis. So
yeah,
covert seems like almost more like restricted than that. So
yeah. So in a way, we're forcing time evolution to be trivial in some cases, because when we say that our identity covariatisms are just a cylinder where we kind of take it and elongate it. And so because this is a functor, it preserves identities. So that's then the identity linear map. So it doesn't change the states. So if we're effectively asking that these time evolutions, just a long time, but nothing else happened, it's trivial. And that's kind of why you're separating it out. So here we get to the funny faces. So the most basic covariatisms we're going to consider are the identity covariatism in the middle, and you have covariatisms from the empty set, which we can kind of just consider as a trivial manifold, two circles, and from circles to the empty set. So the cylinder is our identity map, and the two other covariatisms we have are called unit and co-unit, or identity and trace, because of what they do on matrices. So if we're assigning a circle to a matrix algebra, this here, this takes in a number from the ground field and outputs. The vector it outputs is the diagonal matrix, where the diagonal is just all that number from the ground field. And this one takes in a matrix, adds along the diagonal, and outputs the trace. So if we compose these, we just glue them together and we just kind of get an orb, we have a map we call the quantum dimension, because if you put in one here, it sends it to a diagonal matrix, and then it does the trace, and you just add up one for however many times your dimension is. And this is just the dimension of your states, not the dimension of the TQFT. Here it's always 2 for the TQFT. And here I'm going to denote those eta and epsilon, but you don't really have to worry about that. So the next fundamental covariatism is called the pair of pants. That's the technical term. And this is effectively a multiplication operation. So when we're mapping this from the covariatism category to vector spaces, we're saying that the pair of pants here has to become this linear map from A tensor A to A. So for other reasons, we'll also see this is really strongly similar to multiplication. And if you just flip this diagram, you get this kind of the same thing inverse. You map from A to A tensor A. And so we just call that co-multiplication. Take one value and spit out 2. Any questions about that? Okay, so the first thing that's kind of interesting we can do with this is we can use this covariatism structure to compose some of these weird tube diagrams, and we can actually show that the state space for any topological quantum field theory is finite dimensional. And so what we do with this is we just cap off the multiplication and co-multiplication. And what we get are these bilinear pairings of our vector space with itself. And then we can do this, which all we're doing here is taking this diagram, which we have as this kind of weird bendy thing. And if you literally just geometrically straighten this out in the sense of topology, you can stretch this, show that it's equivalent to this tube. And what that means in our target category in vector spaces, you have this weird composition of maps, this bilinear pairing that ends up being the identity. And if you take this diagram here and you also flip it, these combined being the identity shows that these pairings are non-degenerate, which forces finite dimensionality of our state spaces. So that is a fair bit of linear algebra, and I don't have a proof on hand. Sorry. Anything about that? Sorry? Not so. Yes, in this case we have something from the ground field tensor, something from A, because yeah, so beta here. Yeah, beta here is A tensor A to the ground field, and so our left-hand side here, we're taking an element of A tensor, an element in the ground field. And yes, element in A tensor, element in the ground field, and then we map it through this diagram. Our composition becomes the identity. Sorry? Yes. Yeah, so that's the kind of weird technical detail in the main I'll have a reference at the end of the talk. Joachim Koch's book, Topological Quantum Field Theories and 2D Frobenius Algebras, goes through this in detail. And kind of the main fix for that, I believe, is basically just orientation on these kind of pairings is effectively what you get to show that. You can also think of there just being a trivial, like non-existent map from the ground field to the ground field there, and that should also be identity. Yeah, so our non-degeneracy is kind of from this like reversal of the pairing, the co-pairing. And so this is actually not, this is not dependent on this being two-dimensional. Here I'm showing this specifically as this pairing between the circle and the circle because those are the only things we have. But in higher dimensions, you get the same result where you get these the non-degenerate pairing between your arbitrary V and W vector spaces, and it forces them all to be not finite dimensional.
And that doesn't depend on like
the TQFT, yes. Yeah, okay. So if I take some high dimensional covariatism category, we couldn't even begin to like represent, generate whatever, we still have this result. You can't really draw it. I don't know how to draw a 3 covariatism. I would welcome anyone to try. Yeah, so our next thing we can do with this is also a similar thing where we kind of have this dropping off of the ground field. But if we put these caps onto our multiplication, it's now once more, we can kind of just squish this down. There's no more boundary there anymore. And these are also equivalent to the identity. And so this is effectively showing that here, this is that the unit is actually a unit. So this is 1 times x is always x, but in our multiplication in our TQFT. And this also applies to co-multiplication. You can just flip this entire diagram. And so we have identities in our multiplication. The next thing we can do, show commutativity. So we've now got an abelian monoid, if you know this term. So we can just untwist this, and it's the same as the twisted version. So multiplication is commutative, and co-multiplication is also commutative. our next kind of proof we have here, associativity. Again, you can just switch something down. So if you re-parenthesize an expression, it's the same result. So our multiplication and co-multiplication are now also associative. Oh. Anything but, oh. So the flipping, so when I say flipping, I mean effectively across the vertical axis here, because I'm only drawing these diagrams for our multiplication. So for this data map, sorry, that's not the right one. For what I wrote mu here, so this multiplication, if you flip it across vertically, you get the result for co-multiplication. But when I say that like this is this equality here, it's yes, yeah, basically. The other way, and kind of like the traditional way, is effectively, since these are topological spaces, they are homeomorphic. So these two diagrams, you can continuously map one to the other, and you can have a continuous inverse. And so they're homeomorphic as topological spaces, and they're the same cobordism in this cobordism category. Yeah, I really tried to get an animation or something of these. It was impossible to tix. So our final thing is kind of a weird one, and this is where the title of the talk kind of comes back. So we have this identity here where we have kind of this bendy S with multiplication and co-multiplication, and it's the same thing as just composing the two together back to back. And in order for this to kind of fully be a proof, you need to flip this vertically, show that it's also the same. But so this is a compatibility condition between our multiplication and co-multiplication we have. And it's kind of the final piece in classifying what our TQFT is. So we already know these two TQFTs are entirely vector spaces. They're classified entirely by what they send the circle to. And on here, we've effectively shown that this is an associative algebra and co-algebra, if I remember correctly. And now we've shown a compatibility condition between these two structures. And so it gives us the structure of what's called a Frobenius algebra, specifically a commutative Frobenius algebra. And so there's a couple definitions of this. We have a vector space that's an associative algebra and co-algebra in a compatible way. And I'm just going to use compatible. It's a lot of the heavy lifting here. We have an associative algebra with a monoid and comonoid structure in a compatible way. So that's effectively giving us our normal vector space multiplication. And that is also that's also like our unit and co-unit from before with our pants maps. And the final way you can do this is associative algebra with a linear form satisfying certain properties, but I'm not very good at lineage, and I don't remember that one. So our final thing is, well, oh, I'm sorry, I went past that. So all the definitions have your multiplication and co-multiplication. All are finite dimensional. And in every one, your multiplication and co-multiplication have this compatibility condition, which is called the Frobenius law. You might see this written out in a lot more verbose of a way, but this is kind of like the compact form, which is equivalent. And that is the same thing you can see here, just kind of chop off the right-hand side without the flipped S. Any questions on that? I know that's a lot. So do you know what a monoid is?
Yeah.
Comonoid is when you flip the arrows, but more generally, it is the Yes, so you have a structure where you have a co-multiplication from A to A tensor A, and you have a co-unit, and you have associativity, I believe, for monoid. I should remember that. Yeah, so the co-mon, oops, sorry.
That's kind of backing up that asking about those things. Then what's the actual context?
I really should have made a slide on that. A co-algebra it's once more a similar thing where you would normally have an operation, say addition, multiplication, scalar multiplication. You kind of just flip the arrow of the map.
Okay, so it's kind of like multiplication one operation.
Yeah, so I don't really love the associative algebra in a way. At least personally, I ascribe to the second definition as much as possible because I don't like thinking about a coalgebra, where the one is a lot simpler. It's kind of that inverse pair of pants where you turn one circle into two circles. Yeah, so also just this is the big thing in this classification result, to the point where this diagram is like the icon of the definitive book on it. So everything else is kind of lead up to this. And I really wish I could do more, but I feel like it's very hard to introduce this classification result in a nice way, because at some point you have to be like, okay, also here's what a Frobenius algebra is, because you probably haven't heard of it. Yeah, and so just looking at our previous kind of facts, we have A being finite dimensional. We have multiplication and co-multiplication exist. We show they have an identity, they're commutative and associative, and we satisfy the Frobenius law. And so we can conclude that our vector space, which we assign to the circle A, which characterizes the entire 2D TQFT, is always going to be a commutative Frobenius algebra. And we add commutative here because the normal definition doesn't necessitate that. And we twisted the pant legs. So 2D TQFTs are equivalent to commutative Frobenius algebras. Don't want to quite go to the references. I think I still have time. Would anyone else like to have any questions about that? Yes.
Yeah, I was wondering why, like, one question, not having the
You don't, yeah, so with this, you can't show that there exists an inverse. There are, I'm fairly certain there are TQFTs in which these are group structures and co-group structures, which also similar thing, you flip the maps. But with this, we don't have a cobordism which kind of gets the inverse of another one, and we definitely don't have a way to kind of combine those and get back that cap. So the way we can prove things is composing cobordisms, showing that cobordisms are homeomorphic, and that forces equality of the corresponding linear maps. Probably should have been more clear about that. Anything else?
I guess I'm still just on why it just add why just why there doesn't just have the opposite pair of pants or something.
So the opposite pair of pants. So also kind of implicitly here, we're taking these wrong slide again. Where was it? Yes, sorry. So in our pair of pants, we're kind of reading these left to right. We're saying this is a cobordism from N to N or whatever. So N here is a disjoint of two circles, N here is one circle. If you flip that cobordism, it's not like an inverse. You're just inverting the corresponding linear map. You're not inverting the linear map necessarily. This is another cobordism which gives a linear map kind of in the opposite direction. I don't believe so. So the case here, like if you flip your pair of pants is a linear map from A tensor A to A. And so if you flip that around, you're not getting like the inverse of an element or anything. You're getting a different linear map now from A to A tensor A. Yes. Sorry. So the reason I can't do it like a whiteboard. So so the kind of the one you would expect from this, the really sorry, that's the reason you can't show that is because, for example, if we compose kind of the inverse pair of pants here, what we get now is basically like a torus with two punctures. So we have that, I think I kind of mentioned it before, like a genus one straw, or a genus one identity map. And so there are commutative Frobenius algebras where that identity holds true, and that's actually a very, that's a pretty significant case. But because if we kind of compose these covariatisms here, because it's not homeomorphic to the cylinder, it isn't necessarily isomorphic as a linear map to the identity, so therefore they're not inverses. Is that sufficient? Yeah, so oh, so are you saying effectively, like using kind of the notation I'm saying here, are you saying if we take oh, there's so the reason we can't have that is because that is no longer a cobordism in the sense that our boundary of that manifold is only one circle. It's not the disjoint union of two manifolds in our category. So when we define the cobordism category, we're saying that our cobordisms are one higher dimension manifolds where the boundary is the disjoint union of the two it's mapping between. So the way I'm imagining this, you're almost describing you have a boundary kind of circle and it extends up and then kind of connects to a torus. Or thank you. Yeah, sorry. Anything else?
When along from this, like you're sort of more like you're more standard like quantum field theory, like the state space.
Yes.
So still thinking about like I guess with like a physical analog for why would be like going from like taking like co-product for example with, or I guess like taking the product for example with like collapsing things down into from two to
Do you mean like taking like tensor product of two states?
yeah.
Yes, so that's if we go
Sorry.
a bit back. Yeah, sorry. So so once more, disjoint unions of space-time are inducing tensors of associated state spaces, and that is akin to our standard quantum thing where we take two independent systems and our like kind of total state space is the tensor product of them. We're not really talking about the So this is the mathematical formulation of these, which ends up being very closely related to the physical formulation. The early physical formulations of this are due to Witten, Edward Witten, and I believe he effectively just defined gauge theories where he proved that the action, functional, and whatnot was just completely independent of the curvature form. And then Atiyah and Atiyah, I'm actually not how it's pronounced, I believe both defined kind of this more algebraic version of a quantum TQFT shortly after. The original Witten paper is on reference. Look at it. I guess I can also mention some of the generalizations of this, the really kind of new and spicy one being extended topological quantum field theories. So we can take higher categories in which we have now morphisms between other morphisms. And what this is we have our cobordisms here. It's a higher dimensional manifold where our boundary is lower dimensional manifolds. And for our extended topological quantum field theories, we can take various extended cobordism categories where we have higher cobordisms that are manifolds with corners that are cobordisms between lower cobordisms and lower until eventually you get to whatever kind of your base dimension is you're considering. And I believe a lot of the current research in extended TQFTs is over with Jacob Lurie. And those, it's a very obnoxious definition and it involves a lot of higher category theory, but it ends up encoding locality in your TQFT. Some of the other things you can do with these, if you go up to 3 dimensions, TQFTs have a lot of tie-ins with knot theory, where these kind of linear maps and this structure as a vector space eventually forces, if you have a trivial cobordism from a 3 manifold to the ground field, you're effectively taking some invariance of that 3 manifold. Let's go all the way here. And so here's some references you would like. Anything?
All right. Well, if no one has any more questions, then thank you for the presentation.
Thank you.
I'm certainly not enough of a topologist to have understood it, but I appreciated the being there. There were good diagrams.
Thank you.
Oh, excuse me. Yeah, all right. I think that's about all we have for today. If you have more questions, I'm sure Fiona is happy to answer them. And then next week, since we have a bigger exam week and week before spring break, we're gonna have something a bit more fun. So probably some sort of movie night. We're still deciding for sure, but you should all come for free food and entertainment. And then are you okay if afterwards I post the slides of the recording for Discord
Yes.
for people to see? All right.
Yes, I can. Oh, I already sent.
Yes. Yeah. This is my computer. Yeah. Great.
Cheers. Thank you.
If any of you are interested in giving a similar presentation, the message is for
Let me cut this recording.